So, dear student, good afternoon, good evening to all of you. This is in continuation to the last lecture. We were discussing about problems of supply and availability of nutrients. Or in this part, we tried to understand what is soil solution, what is the concentration of different nutrients in soil solution. And I suggested you, this is the reference for further studies, chapter 2 in Havlin book. And we discussed different definition of soil solution. We have seen the importance of soil solution. We have seen that concentration of nutrients in available form is very, very small, which is there in soil solution. And we have seen the sources of nutrients into the soil solution. Means buffering of soil solution happens through three important sources, either from minerals or from exchangeable or from non-exchangeable forms. And you have also seen that the fraction of soil solution, nutrients in soil solution is very small. For example, in case of potassium, only 0.1 to 0.2% potassium is in solution form. And we discussed the importance or value of soil solution. And then we have seen how the nutrients are compensated or replenished in the soil solution, and what is the fate of nutrients. They can go for leaching, they can be taken up by microbes, or they can be precipitated. There are several pathways for losing nutrients from soil solution, and also nutrients are replenished through different sources. And you have seen these sources already. You can see soil minerals, exchangeable cations, anions, chemical compounds, and organic matter are the sources to supply. And you have also seen this picture. This tells input and output from the soil solution. And we have also seen how the nutrients are classified into different forms: readily available, moderately available, and slowly available. And I have given the example of phosphorus, where you have very low availability, particularly when mineral phosphorus is there, and very strongly adsorbed phosphorus. And you see high availability is for H2PO4 and HPO4. And one of you answered that at pH 7.2 or 7.3, this proportion of H2PO4 and HPO4 is equal. What is that pH? 7.2 or 7.3?
7.2, sir.
7.2. Now we have seen that how the nutrients are cycled in soil, means input, output. And then we were discussing the factors that affect the nutrient availability, or factors that solve the problem of resupply of nutrients into the soil solution. So these are the factors: mobility of nutrients in soil, CEC and AEC of the soil. Means generally, for example, if a nutrient is mobile, so it can be easily accessed by the plants because it is uniformly distributed in the soil layers. But if it is immobile, then its availability is restricted to a smaller area of the soil. Higher CEC, higher AEC means higher nutrient supplying capacity to the soil solution. Base saturation, generally higher values of base saturation will saturate the soil solution quickly compared to the soils which have less base saturation. Similarly, buffering capacity. Buffering capacity of the soil varies with the texture and structure of the soil. There are many factors that affect the buffering capacity of the soil. Here, buffering capacity means the nutrient supplying capacity of the soil into the soil solution. Soil pH of the soil solution is very, very important. It affects the nutrient availability. It affects the solubility of the nutrients also. And it also regulates the activity of the microbes in soil. Then soil organic matter and its decomposition by microbes, it also influences the nutrient availability into the soil solution. And physical conditions of the soil, physical properties like water holding capacity or water in soil and some other temperature, they are going to affect the availability of nutrients in soil solution. So these factors we are going to discuss in detail. So let us see what is mobile nutrients. So mobile nutrients are normally nitrate, sulfate, chloride, and boric acid. It has no charge. It is having just in acid form. So they are not strongly attracted to exchange sites. They are soluble in soils, therefore they readily move through the root zone. These anions. Of course, some of the anions are also attached to the colloids, soil colloids. Whenever I say soil colloids, these are inorganic colloids, which are clay minerals or which are clays. And also your organic colloid is your humus. So these colloids, overall, they have negative charge, but that does not mean that they do not have any positive charge. They also got positive charge. So to the positive charge, negative ions or these are anions are attached, and negative charges wherever are there on humus or clay colloids, then negative charge attracts the cations. So it is simple, and therefore you have cation exchange capacity and anion exchange capacity. So mobile nutrients within the whole soil volume occupied by the plant root system are available for transport to the root in percolating and transpirational water. As you know that in soil water moves, so these mobile nutrients can easily move along the water or through the diffusion, and they can be easily accessed by the roots. Relative mobility of each nutrient depend upon soil pH, because soil pH can affect the mobility. For example, particularly in case of phosphorus, the mobility is low because of either lower pH or either higher pH. It precipitates or it fixes phosphorus. Temperature also affect mobility, moisture, soil texture, clay type, and organic matter content. We will discuss how they are affecting the relative mobility. Here means movement of nutrients or ions in the soil. Now let us see what is about immobile nutrients in soil. Immobile nutrients interact with mineral and organic matter surfaces, are less soluble, do not readily move throughout the root zone. So they are not easily moving from one place to another place, or rather they move very slowly. Therefore, they are called as immobile nutrients with respect to soil. Relative immobile in soil means one is immobile, other can be relative immobile in soil. Plant roots access these nutrients from a small volume of soil surrounding individual roots. So therefore, in most of the cases for phosphatic fertilizer, it is suggested to place them in a narrow band so that they are put or they are kept near the seed or they are kept near the roots, because roots cannot explore the whole volume of soil. So it is better to keep these fertilizers near the seed or near the roots or below the seed, so that the roots can easily access such immobile nutrients. Plants create a small zone around the root that has very low concentration of these immobile nutrients due to plant uptake. So of course, whatever nutrients are there, particularly immobile nutrients around the roots, they are easily taken up by roots. Then the concentration of this nutrient becomes lower in the root zone. The concentration gradient then allows diffusion to transport nutrients that are further away from the root surface towards the root. So whenever there is shortage of nutrients around the roots, they will diffuse from higher concentration to lower concentration. If the soil has high buffering capacity for an immobile nutrient, then the solution can be replenished and diffusion continues. So this is important. You can see if the immobile nutrient has high buffering capacity, like your potassium, so the solution can be replenished and diffusion continues. With a low buffering capacity, solution concentration and diffusion ultimately decreases, causing a nutrient deficiency. So you can see for the movement of nutrients from bulk soil to soil solution is affected by this base saturation or buffering capacity of the soil. The important points for nutrient mobility in soil are, overall, what can be said about the nutrient mobility in soil? Number one, the mobile anions, sulfate, nitrate, chloride, quickly move through the root zone with water. So they move faster, therefore their leaching is also high. The mobile nutrients are available within the whole soil volume uniformly because they move from one place to another place, and their concentration gradient is harmonized. Means they will have almost uniform concentration or content throughout the plow layer. The immobile nutrients interact with exchange surfaces and are less soluble and move slowly through the root zone to the root surfaces, like phosphorus and potassium. Ammonium, potassium, calcium, magnesium are more soluble. Of course, they are less mobile. Ammonium, potassium, calcium, magnesium are more soluble and mobile than micronutrient cations H2PO4 and molybdenum. So you can see that the fastest moving are your anions, sulfate, nitrate, and chloride, etc. And then next in order are ammonium, potassium, calcium, magnesium. They are relatively less mobile and almost immobile. Nutrients are your micronutrients, cations, your iron, manganese, copper, etc. And H2PO4 are very less mobile and molybdenum. So you can remember the order of mobility of nutrients. The knowledge of nutrient mobility is useful in deciding the nutrient management practices. So why we study the nutrient mobility? Because it can help us to decide the method of fertilizer application. For example, nitrogen fertilizer or nitrogen, you have seen it is mobile in soil. So therefore, nitrogen fertilizer can be broadcast. Top dressing can be done or basal dressing can also be done for nitrogenous fertilizer. But other fertilizer like phosphatic fertilizer, you need to place them in beds or near the roots or below the roots in the soil. Because you know that phosphorus will not go to the roots. So therefore, it is better to bring roots to the phosphatic fertilizer. Now, so you have seen how the mobility is affecting the nutrients availability. You have seen that the availability of anions is throughout the whole horizon uniformly, but in case of certain cations, like micronutrient cations, they move very slowly. So they cannot be replenished easily in the soil solution. The clays and humus, now let us see how this cation and anion exchange capacity of the soil affect the nutrient supply to the soil solution. So generally, you see if you have higher cation or anion exchange capacity, the ions which are adhered, which are adsorbed to these colloids, if they are higher in number, higher capacity, then replenishment will be more. If your cation or anion exchange capacity is low, then the buffering capacity of soil will be low. So clays and humus work as soil colloids, as you know. These are exchangeable sites. The ions which are attached to clays and humus are exchangeable ions, maybe cation or anion. Absorbing the cations and certain anions, cation and anion exchange occur in soils between soil solution and exchangeable sites. So exchangeable sites, you know, these are colloids. So now know more about cation exchange capacity and anion exchange capacity. Ion exchange is reversible process. Reversible process means the ions can be removed or can be transported from exchangeable sites to the soil solution, and they can go back also. And they need to be in equilibrium. They need to be in equilibrium. Whenever there is shortage of ions in the soil solution, they may come from the exchangeable sites to the solution. And whenever there is shortage of ions, or say concentration of ion is less on exchangeable sites and it is more in soil solution, then they can go back to the exchangeable site. And this is for individual ion. One ion will have exchange with the same species of ion. cation exchange is more important as the cation exchange capacity is larger than the anion exchange capacity in soils. And otherwise also, you see the species of anions are less in number. It is chloride, it is sulfate, it is nitrate. But most of other ions are cations. So therefore, in soil also, nature has made cation exchange capacity as higher than the anion exchange capacity. So therefore, cation exchange capacity is more important than anion exchange capacity in soil. This process enhances availability and retention of plant nutrients. Because higher the cation exchange capacity, the retention of nutrients or ions will be higher. If the cation exchange capacity is low, then leaching of cations can also occur. As I was referring yesterday, that ammonium leaching can also occur, potassium leaching can also occur. Now, soils dominated by oxides of aluminium have positive sites in acidic soils, and anions can be adsorbed and dissolved from them. So here, this slide will prove that anion exchange capacity of the soil increases with a decrease in pH. As soil pH decreases, anion exchange capacity increases. Or in other words, as soil pH increases, anion exchange capacity decreases. So in acid soils, oxides of aluminium have positive sites in acidic soils, and anions can be adsorbed and dissolved from them. So here the positive charge is more. Positive charge is more in acidic soil. Therefore, anion exchange capacity is high. Nitrate and chloride are weakly held at positive sites of soils, soil colloids, and more likely to be found in soil solution, particularly under acidic conditions. H2PO4 and sulfate are strongly bound to exchange sites. They are strongly bound to exchange sites. Anion exchange capacity increases as soil pH decreases, and AEC is much higher in acid soils. Now, cations and anions on soil exchange surface. The quantity, how much quantity of cations or anions are there on the exchangeable sites. Exchangeable sites can be referred as soil exchange surface. Except for aluminium and sodium, most of the exchangeable cations are plant nutrients. You already know, what is base saturation also. In acidic soil, principal cations are aluminium, hydrogen, calcium, magnesium, and potassium. Of course, aluminium and hydrogen dominate. Whereas in neutral and basic soils, the predominant cations are calcium, magnesium, potassium, and sodium. Cations are adsorbed to the CEC with different adsorption strength. So CEC, these are exchangeable sites. So cations are adsorbed to the CEC with different adsorption strength. Adsorption strength may be different for different cations, and this strength will affect their availability or their replenishment to the soil solution. So let us check that which cation has the strongest affiliation or strongly attracted to the exchangeable surface. So can I ask a question? Can you tell me the cation which has highest adsorbing strength? Cation.
Aluminium.
Aluminium, correct. And then next?
Hydrogen.
Correct. Hydrogen. Next?
Calcium, then magnesium, then potassium.
Correct. So you see as the valency of the cation is decreasing, its attraction force or adsorption strength is decreasing. Higher the valency of the cation, higher is the adsorption strength. But see, case of hydrogen, it is having only one valency, but still it is before calcium and before magnesium, although these calcium, magnesium have two plus charges. You told me that aluminium is number one, highest adsorption strength, followed by hydrogen, calcium, magnesium, potassium, sodium, etc. Then Why hydrogen is in between aluminum and calcium, or 3 plus 3 and plus 2, though it is plus 1.
Sir, high charge density.
Correct. Hydrogen has high charge density per unit weight. Per unit weight, it has very high charge density. So it is strongly adsorbed to the exchangeable surface. So cations are adsorbed to the CC with different adsorption strength, influencing the ease with which cations can be replaced or exchanged with other cations. Now you see cations and anions on soil exchange surface. For most minerals, the strength of cation adsorption is like this. So you see aluminum, then hydrogen plus 1, calcium, magnesium. Potassium is almost same to ammonium. Potassium have equal strength. And then sodium is the last one here. So you can see the properties of the cations determine the strength of adsorption or ease of desorption. How easily they can be dissolved or how strongly they are attached. Hydrogen ion is unique because of its very small size and high charge density. You were right. Its adsorption strength is between aluminum and calcium. So it is natural that the ions which are easily exchanged, their replenishment or buffering will be fast into the soil solution, and cations which have very strong attachment to the exchange sites, they will go slowly to the soil solution. So adsorption strength for cations with similar charge is determined by now within calcium and magnesium, or within potassium or sodium, how we will decide the adsorption strength. So adsorption strength for cations with similar charge is determined by size or radii of the hydrated cation. They can absorb water, they can get hydrated. So what will be the size of the radii or radius? As size of the hydrated cation increases, the distance between the cation and the clay surface increases. So normally larger hydrated cations cannot get as close to the exchange surface as smaller cation, resulting in decrease in strength of adsorption. Means more the hydration, less is the attraction, less is the adsorption strength. Cation exchange capacity, we'll see them separately now, cation exchange capacity and anion exchange capacity. CC is one of the most important soil chemical properties influencing nutrient availability and retention in soil. Soil CC represents the total quantity of surface charge on minerals and organic matter available to attract cations in solutions. So I need not to repeat. This is how cation exchange capacity is defined. So now we can go to the second link, please. Now I am stopping share and we can go to second link. I'm ending this. So please join the. So we were discussing about cation exchange capacity, and what is cation exchange capacity? It is amount of cations that a particular weight of soil can handle. And milliequivalent, it can be expressed in milliequivalent or milligrams. This is expressed as milliequivalent. Somebody's mic is on, I think. So now CC is expressed as milliequivalent of charge, negative charge, per 100 gram of oven dried soils. The milliequivalent unit is used instead of mass because of CEC represent both the milliequivalent per 100 gram of negative charge and the total milliequivalent per 100 gram of cations adsorbed to the CEC. Now we go to the anion exchange capacity. This is also important to supply the nutrients to the soil solution. Anions, particularly in soil solution, are adsorbed to charged sites on clay mineral edges and organic matter. As you know that soil colloids have both kind of ions, cations as well as anions. but quantity of anions is very small in on exchange surface. Anion exchange may also occur with OH groups on the hydroxyl surface of kaolinite. So as you know, these kaolinite have 1:1 structure. Displacement of hydroxyl from hydrous iron and aluminum oxides. You know what are hydrous aluminum and iron oxides? Suraj? Can you tell me formula?
Yes, sir.
Just tell me about what is iron oxide hydroxide.
OH minus, sir.
OH minus. No, I'm asking formula. Formula of iron oxide.
FeO3.
FeO.
Three.
There are 2-3 different kind of oxides of iron. They have different values.
Fe2O3.
Okay, Fe2O3. FeO is also there. So displacement of OH from hydrous. So then what is hydrous? Hydrous means water is added. Hydrous means water is added to the iron or aluminum compounds or oxides. That is the meaning of this. Displacement of OH from the hydrous means hydrated iron and aluminum oxide is also an important mechanism for anion exchange, particularly in highly weathered soils of the tropics and subtropics. Anion exchange capacity increases as soil pH decreases. We already discussed it. Further, anion exchange capacity is much greater in acid soils, high in 1:1 clays, that is kaolinite, and those containing iron and aluminum oxides than in soils with predominantly 2:1 clays. So you know, in acid soils, these iron and aluminum oxides, they dominate, and they also got some positive charges. Therefore, they attract the negative charges or anions. And montmorillonite minerals usually have an AEC of less than 5 millicoulomb per 100 gram. So you can see that 2:1 type of clay mineral have very low anion exchange capacity, just 5 millicoulomb, whereas kaolinites can have AEC as high as 40 millicoulomb per 100 gram at pH 4.7. So as you can see, at pH 4.7 means under acid conditions, your montmorillonite have very less anion exchange capacity than kaolinite type of clays. Anions such as chloride and nitrate may be adsorbed, although not to the extent of S2PO4 and sulfate. So they are strongly adsorbed, this S2PO4 and sulfate, than chloride or nitrate. The order of adsorption strength of anions is S2PO4, then sulfate, HNO3, and chloride. So you can remember this sequence of adsorption strength with respect to anions. Now you can see this figure. This is quite interesting figure. You can see in the central box, you got soil solution, and nutrients are present as anions and cations, and they are considered as in available form. So they can be taken up by the plant roots, uptake of anions and cations, but some anions and cations are also added by plant roots to the soil solution. Similarly, these nutrients can come, number 2, you can see the lower box, soil colloids, that is clays and humus, and they have got adsorbed cations and anions. So these are exchange surfaces, and from here, the ions can exchange into the soil solution. And you can see most of the time a balance is maintained, or kind of equilibrium is maintained. So exchange of cations and anions between soil colloids and soil solution and plant roots, arrows 1 and arrow 2. Cations of soil solution exchange for hydrogen and anions for hydroxyl produced by roots. Exchange of cations and anions continue till an equilibrium is reached. So try to understand this picture, very simple to explain. Now, the third factor, we have seen that how this cation and anion exchange capacity affects the nutrient supply. And we have also seen mobility, how mobility of the nutrients will replenish or affect the resupply of nutrients to the soil solution. Now, third important factor or point is base saturation in soil. So you know already we discussed what is base saturation. We also discussed about some other aspects, but I asked you one question yesterday. What is amphoteric? Soil has amphoteric property. What is amphoteric property? I gave you homework yesterday.
So those substance which is having both acidic nature and basic nature.
Correct. So in case of soil, instead of substance, we can say soil. So soil has actually that property, amphoteric property. So it can act as a base. It can also act as acid. Now, base saturation in soil. It is percentage of the total CEC, total cation exchange capacity, that is occupied by calcium, magnesium, potassium, and sodium. So these are 4 cations. They are called as base cations, basic cations. The base saturation is higher in soils of arid region than the humid region, because naturally in humid regions your calcium and magnesium are lost by leaching because of high rainfall. So there the salt concentration or concentration of these cation is less, so their concentration is more in arid region soils. The increased base saturation in soil increases the availability of cations, calcium, magnesium, and potassium. So higher base saturation means higher availability of calcium, magnesium, and potassium, which is mostly under arid region. In general, higher the base saturation, higher is the availability of cations in soil. So this is important point. Therefore, you can see that base saturation is affecting the nutrient supplying capacity or nutrient availability. Now, buffering capacity of nutrients. So the ability of soil to resupply ions into the soil solution from different sources. So what are sources? Your colloids. So how quickly, how readily the nutrients can be supplied or replenished into the soil solution. That capacity is known as buffering capacity. So it can be defined as, so now you can define it as the ratio of the concentration of the adsorbed ion and solution. So buffering capacity can be for individual nutrient also. So it is concentration of the adsorbed ion and solution ion. So what is the proportion of these two or ratio of these two, quantity and intensity? Soils may vary in buffering capacity. Some may have more and others may have less. So buffering capacity varies. So normally higher the buffering capacity, higher is the replenishment of or higher is the availability of the nutrients. So generally buffering capacity in soil increases with increasing CEC. Higher the CEC, higher is the buffering capacity. Higher organic matter and other soil constituent in soils. Buffering capacity of Mount Morillonite clay, high organic matter soil is greater than that of kaolinitic, low organic matter soil. So you can see the buffering capacity is more when you have higher Mount Morillonite clay and higher organic matter than the kaolinitic and low organic matter soils. Since CEC increases with increasing clay content, fine texture soils will have higher buffering capacity than coarse textured soils. Is it clear? This CEC increases with increasing clay. This is correct. And naturally, fine textured soils have more clay. Therefore, they will have higher buffering capacity than coarse textured soil. If exchangeable K ion, potassium ion decreases by plant uptake, suppose this is an example, plant uptake is happening and it is taken from the soil solution or it is lost by leaching. The capacity of the soil to buffer solution K is lower in sandy soil. Lower in sandy soil because its CEC is low. So less quantity of potassium is absorbed on the exchange surface. The nutrient may become deficient and K fertilizer will be needed to increase the exchangeable K and correct the K deficiency. Therefore, these days now people are talking about split application of potassium, particularly in light texture soils. The split application of potassium is suggested. Even in case of nitrogen, if you see the case of wheat, in case of wheat, if your soils are heavy texture or fine texture soils, you need only 2-time application. Half nitrogen can be applied at the time of sowing and half can be applied at first irrigation. That is enough. That is recommendation according to the soil texture or the clay content. But if your soils are light or sandy loam soils, then you should go for at least three split application. So lighter the soil, you need to go for more split application of nitrogen. But now for rice and wheat, potassium split is also recommended, particularly in soils which have low cation exchange capacity. So nutrients may become deficient and potassic fertilizer will be needed to increase exchangeable potassium and correct the potassium deficiency. Addition of phosphatic fertilizer will increase adsorbed phosphate, H2PO4, while some H2PO4 may also precipitate as solid phosphate compounds, both of which contribute to the phosphorus buffering capacity in soil. So therefore, you see many times we got residual effect of phosphatic fertilizer. Wherever we apply phosphatic fertilizer or water-soluble phosphatic fertilizer, it is quickly converted into unavailable forms. And then it is sometimes in readily available form, very small fraction, sometimes moderately available, and then less available or insoluble phosphatic compounds are made. Addition of P fertilizer will increase adsorbed H2PO4, while some H2PO4 may precipitate as solid P. So both are the source of phosphorus. One is exchangeable source, which is on the exchange surface, and other is non-exchangeable phosphorus. And that can be solubilized. That can be solubilized to supply phosphorus. Thus, it is evident that buffering capacity is very important soil property that strongly influence nutrient availability. Like other property, mobility, your cation exchange capacity, buffering capacity is also important. If same rate of fertilizer P is added, now you see this is very interesting question. If same rate of fertilizer P is added to both soil, to two kind of soils, the resulting solution H2PO4 concentration will be greater in sandy than in clay soil because of high buffering capacity of the clay than the sand. So here you see sand will also have low cation exchange capacity. Low cation exchange capacity, it will also have low P fixation capacity and absorb less phosphate on cation exchange capacity. Thus, more phosphate in soil solution than clay soil at the same P application rate. So application rate is same because your clay soil will have more retention of phosphorus on exchangeable sites. Alternatively, if we wanted to establish the same solution P concentration in both soils, then more P fertilizer would be needed in the clay soil compared to the sandy soil. Again, because of high buffering capacity of the clay than buffering capacity of the sand. So this is how this, you see this, we can relate these buffering capacity properties to the fertilizer application rate. Now, next is number 5 is soil pH. How soil pH is going to affect nutrient availability. I need not to go into much details, but I think most of you are aware of the role of soil pH in nutrient availability. Nutrients become less available to crops when soils are too acidic or too alkaline. You already know that most of the nutrients are available in the range of pH, say 6 to 7.5. So what happens if your pH is too acidic or pH is too alkaline? Then naturally the nutrient availability will be affected. If soils are too acidic, availability of calcium, magnesium, and potassium decline, means they cannot be supplied or replenished quickly into the soil solution. But availability of aluminum may be in excess, iron may be in excess as you decrease the soil pH. So if soils are too alkaline, then iron, manganese, zinc, and copper availability become less. And what about molybdenum? Molybdenum and boron. In which pH range they are most available? Boron and molybdenum. Hello?
So, more than 8.
More than 8?
Yes, sir. Up to 10 more molybdenum is available.
Yes. Means irrespective of the pH, alkaline pH, it is almost uniformly available beyond 7 pH up to 8 or 8.5. So in under alkaline condition, mobility, this molybdenum availability is not an issue. But what about boron? Is it more available under acidic pH or alkaline pH, or say from acidic to slightly alkaline? Anybody? Soil science? Is there anybody from soil science? Ashita, you are from soil science? Ishita. Hello?
Yes, sir. Yes, sir.
Yeah, you are from soil science. So you tell me, at what pH this boron is most available?
Sir, between pH 5 to 7, the availability of boron increases, but after pH 9, its solubility, like after pH 8.5 or 9, the solubility again
Okay.
decreases. It is
Okay.
most available in between 7 to 8.5.
Good. So now you see this, if soils are alkaline, your iron, manganese, zinc, copper may become less available. And you already know about availability of phosphorus, how it is affected by soil pH. And I want to teach you phosphorus in detail. I wish to take 2 lectures on phosphorus. So then I will teach you all these points. They are very, very important points. So far, phosphorus availability is concerned. Now, the 6th point is how soil organic matter and its decomposition by microbes will affect the nutrient availability. It is quite natural also that higher the soil organic matter, higher microbial activity will increase the nutrient availability. Availability of nutrients from soil organic matter depends on microbial activity, and the factors which affect the microbial activity, microbial action, will also affect the nutrient availability or decomposition rates. Important microbial processes are organic matter decomposition and denitrification. Fresh plant or other organic residues are subject to rapid decomposition, and they release the nutrients. And also it helps in 2 ways. One is that it is the source of nutrients, and secondly, it also gives us humus, and which can absorb the ions and keep them for plant availability. In virgin uncultivated soil, the organic matter content is determined by soil texture, topography, and climatic conditions. So we need to see under what conditions we can have higher levels of organic matter in soil so that nutrient availability is improved. So in uncultivated soil, organic matter content is determined by soil texture, topography, and climatic conditions. Organic matter content is higher in cooler than in warmer climates, and with similar annual temperature and vegetation increases with effective precipitation. So you can see that there are a number of factors that affect the organic matter content in soil. First is your temperature. Normally, under cooler condition, you can have higher organic matter than warmer conditions. And similarly, if you have temperature and rainfall or moisture are another factor. If you keep the temperature constant but increase the moisture percentage, then also you can have higher organic matter content in the soil. Why it is so? These differences are related to reduced potential for organic matter oxidation in cooler temperature and increased biomass production with increased rainfall. So you see under this cooler or warmer condition, how this organic matter is affected. And it is actually interaction of factors. Interaction of factors means your soil texture, your temperature, and as well as your moisture in soil. So one cannot draw universal conclusions. So you need to see all these factors, interaction of all these factors, then one can decide that what will be the organic matter level in soil. So soil organic matter content is greater in fine texture soils. So many times, on an average, under identical conditions, you will find that fine texture soils have more soil organic matter than coarse texture soils. And why it is so? It is related to increased biomass production in fine texture soils. In fine texture soils, you will have increased biomass production. And why this increased biomass production? Because these fine texture soils will have higher water storage and higher nutrient storage because of higher cation exchange capacity. And therefore, they will have higher organic matter content. And furthermore, in fine texture soils, because of higher moisture, the oxidation of organic matter is also slow. Reduce organic matter oxidation potential. So see, many factors interact to maintain a particular status of organic matter in soil. You need to read or study in detail one chapter on soil organic matter in Nature and Properties of Soil, or you can read from Havlin book, Soil Fertility and Fertilizers. Soil organic matter contents are higher under grassland vegetation than under forest cover. This point is also important. Under grassland conditions, you have higher soil organic matter than under forest cover, mainly because of CN ratio. These grasslands or grasses have higher CN ratio than the forest cover. These relations are generally true for well-drained soil conditions. Under poor drainage, aerobic decomposition is impeded and organic residues build up to high levels regardless of temperature or soil texture. So whatever may be soil texture, whatever may be the conditions, but under comparable conditions or under identical climatic and soil conditions, you have two sets of soil. One is aerobic soil, other is anaerobic soil or flooded soil. So in flooded soil, you will have more organic matter content than aerobic soils, mainly because of slow decomposition of organic matter under anaerobic conditions. Now, soil organic matter comprises organic material at all stages of decomposition. You know it, starting from freshly added matter up to the humus. All are included in soil organic matter. Crop residue degrade through autotrophic and heterotrophic microbes and ultimately result in humus. Size of these components depend on climate, soil type, and soil and crop management, all of which influence the quantity of crop residue produced and returned to soil. So overall, we need to understand the details of soil organic matter and its contribution in nutrient supply. Fresh plant or other organic residues are subject to fairly rapid decomposition. Why rapid decomposition? Because they are rich in water, their moisture content is high. So organisms which attack these freshly added matter like to get some moisture also, besides getting nutrients. And also chemical degradation is also faster. Relatively small heterotrophic biomass, 1 to 8% of total soil organic matter, represents soil microbes and fauna responsible for the majority of inorganic transformation that influence nutrient availability. So finally, not only soil organic matter, but the activity of microbes. There may be sufficient organic matter in the soil, but there is no ideal temperature or ideal water conditions, moisture conditions. Then these microbes may not work effectively. So then the nutrient supply to the soil solution may be affected, adversely affected. Soil humus, the largest component of soil organic matter, is relatively resistant to microbial degradation. So normally higher the humus, higher is the cation exchange capacity, anion exchange capacity, higher are most of the soil properties improved. Then finally, this humus is going to improve the nutrient availability in the soil solution. Now you can see the primary soil microbial processes involved in fresh residue and organic matter turnover or cycling. You can see that the nutrients complex in decomposable organic matter, maybe in proteins, carbohydrates, a variety of compounds are there, and they can go for mineralization, and inorganic nutrients are released into soil solution, and humus is also released. But it can happen many times, it can be immobilized by microbes. The nutrients which are in inorganic form can be immobilized by the microbes. However, they will be further mineralized to give you nutrients. In the decomposition process, soil organic matter gives you nutrients. If there are insufficient nutrients in soil organic matter to meet the microbial demand, then inorganic ions are also consumed. So then the supply will be reduced. The microbial activities and rate of release of nutrients from soil organic matter is affected by CN ratio of soil organic matter, soil moisture, soil temperature. So number of factors are there. You are advised to read chapter on soil organic matter, but if you are interested, I can teach you soil organic matter in 2 lectures in much detail, which is also important part. If demand comes from your side, I can do it. Here, can anyone tell me the relationship between CN ratio and decomposition rate of organic matter? Means you have added 2 different kind of material having different CN ratio. One is having wider CN ratio, say you have added grass residues, and other is legume residues, which have narrow CN ratio. So under what condition you will get faster decomposition and why? Yes, Aman. Aman. Bipasa.
Yes, sir.
Yeah, you tell me. Did you listen to the question?
Yeah.
So you can
Yes, sir.
Aman first. Yeah.
Sir, if CN ratio will increase, then the decomposition rate will decrease because there is a low content of nitrogen, so microorganisms are not able to decompose it faster.
That means immobilization of nitrogen is happening.
Yes, sir, immobilization take place.
Okay. So overall, once the decomposition process is over, in both cases means in one case CN ratio was wider. Someday, whatever ratio may be there, it is going to be broken down. Of course, it may take longer time. So will the nitrogen status change in the soil? Aman? Ultimately, finally, once your residues are decomposed, in both cases, whether it was CN ratio was narrow or wider, finally they are
Yes,
going
sir.
to be decomposed. So what will happen
Yes,
to
sir.
nitrogen status?
Sir, can you repeat the question?
See, in one plot, in one field, under identical condition, you have added CN organic material which was having wider CN ratio. Okay. In
Yes.
another plot, you have added organic material, same quantity, which was having narrow CN ratio. So
Yes, sir.
finally, the decomposition may happen quickly under legume
Yes.
residues than cereals.
Yes.
But
Yes, sir.
whatever time it may take, but it is going to be decomposed under both situations. So what will happen to nitrogen status in soil?
Sir, which have higher CN ratio will have lesser nitrogen content.
Which have, yeah. But under both cases, will it increase or decrease?
So when
Under-
complete decomposition takes place, then it is ultimately increases.
Increases. That is what I
The
asked.
CN ratio just tell about the time of decomposition.
Correct. So just I wanted to know, and you replied well, that for others also means whatever CN ratio may be there, ultimately it is going to be decomposed and it will raise the status of not just nitrogen, it will raise the status of other nutrients also. It is so simple. I think you thought that it is very tough question. It was just same question, you know, somebody was speaking that about H2O is doing this, H2O is doing this, and people did not know formula that this H2O is actually water. So it was very simple question. You thought that there can't be such a simple question. Anyways. Now last part of this lecture is physical conditions of the soil will also, or last factor, 7th number factor, the physical conditions of the soil will also affect the nutrient availability. Poorly structured soils, the soil erosion by runoff, you can have under those conditions, nutrients can be lost by soil erosion, runoff, or leaching. Soil microbes and organic matter can also take up your nutrients, immobilization. Soil erosion decreases cation exchange capacity. Poor soil structure restricts the root growth and thus reduces excess of available nutrients. Optimum level of soil water means a higher level of most nutrient in solution. Too much of water means leaching can happen. Soil solution can lose the nutrients, and too little water means concentration of nutrients will be higher in soil solution, and then availability of nutrients will be reduced. Adequate moisture also increases the rate of soil organic matter decomposition. Poorly drained soils increase the solubility of minerals, making them sometimes toxic. Poor drainage. You know about case of rice. Nitrates can be lost due to denitrification in flooded soils. So these are all physical conditions with respect to water, with respect to texture and moisture content. It can result in reduced nutrient availability because water has number of rows. So may I invite your questions and end my lecture today. Pramod. Everybody is sleeping? All right. So we meet tomorrow at 5.
Okay, sir.
Okay, sir.
Thank you very much. So I think you are ready to cooperate and I'm ready to teach you.
Thank you, sir.
I will teach you phosphorus. First, tomorrow I will start teaching phosphorus, which is very important nutrient. And a lot of questions are asked on phosphorus. Phosphorus in plant, how it behaves in plant, phosphorus in soil, how it behaves in soil, and then phosphorus in fertilizer. There will be 3 parts of this. And if time permits and your interest is there, I can have 1 or 2 lectures on soil organic matter, which is also very important. So thank you very much. Bye for now. And may I take your attendance? Attendance will be marked for those who are available on the videos. So can you open your videos? Okay. Abdul, can you take a snapshot and send to me? I don't know how to take this snap online.
Okay, sir.
Will you do this attendance? जिसका वीडियो नहीं खुलेगा उसका अटेंडेंस नहीं लगेगा। Friends, it is not to punish you. I am not punishing you. I am trying to help you. Whatever is my capacity, my limit, according to that, you don't take otherwise. It is not punishment. It is for you.
Yes, sir.
Do you understand what for I am here? Coming to office, taking class, leaving my family in home. I could have also enjoyed my TV. ठीक है, ऐसा नहीं है। ऐसा हो सकता है कि बहुत अच्छा रिजल्ट ना मिले, लेकिन कुछ तो मिलेगा। सो ऋतिक का रहना,
सर
संजीव
मैं और अमन एक ही इसमें हूँ।
है,
मैं और अमन एक से ही ज्वाइन किया हूँ।
ठीक है, आप भेज देना फोटो आपके टर्न। थैंक यू वेरी मच, हैव अ नाइस टाइम, बाय फॉर नाउ।
Thank you, sir.
ओके,
Thank you, sir.
Thank you, sir.
बाय बाय।
Abdul.